Today I want to talk about a favorite topic of mine, which is simulation. And just coincidentally, on Friday the 27th, which was yesterday when I'm recording this, we released the 200th release of Onshape, which included many things, as you can see here from the forum post. But one of the things that we did release was an improvement to simulation, which is the inclusion of inertial relief option for linear static simulations. Now, the 1.5 minutes here is really not time to go into it in any great detail. Neil did a good job with the in the What's New posting here, but I've got a few more minutes to spend with you, and so if you want to strap in and listen to me talk about this topic, then you're in the right place. Now, inertial relief, like FEA in general, has been around for a long time. It's a common theme. If you have a look up in any of the YouTube videos, you look up inertial relief in the various systems like Abacus and Nastran. Here's an ANSYS one, here's one in HyperWorks and OptiStruct. You know, everybody has got these canonical examples of what inertial relief is good for, how you use it, what sort of results, what sort of the limitations and things like that. So I'm not going to recover all of that ground. This is already done really well in here. And also these respective systems have got help that you can check. And if you want to look at the theory behind it, you know, there's certainly a lot of textbooks that go into that. But you know, one of the difficult things with most people using inertial relief is they're not quite sure when and how and where they should be using it. So that's what I want to try and cover today. And also what I do want to cover also is some of the maybe surprising things to some people about how easy it is to do in Onshape Simulation. So we'll get to this guy in a minute, but let's start with this canonical example, and I call it canonical because it's nearly in every textbook about inertial relief. So let's wind it back all the way to this beginning here. Now, if we take this canonical aircraft and pretend that we want to simulate the effect of some force off axis, maybe it's pointing down, and like in this case, we want to see what the result of this on the rest of the aircraft is. Now, of course, the problem is, unlike most FEA and linear static simulations that you've been familiar with up till now, it's not clear where the constraints are. Now, if we just talk about linear static analysis for a second, it's static for a very good reason, meaning the loads are balanced out to zero, and in order for that to happen, most of the time, in fact, let's say all of the time, you have to have a constraint somewhere in the model to stop it moving in a rigid fashion. Right? So rigid motion is there's no deformation, it's just going to freely move in one of the canonical directions, one of the three rotations or three translations for a single body like this. Now, in order for a linear static analysis to work, you have to stop that rigid body motion. And generally what you do is use constraints, right? So you pick a face or a node or some other thing in your model, and we're talking general FEA here. I'm not doing an Onshape simulation tutorial yet. In general FEA, you pick a node and constrain it in certain directions, and then you might have to pick another node and constrain it in certain other directions, and you may probably have to pick one more node to constrain it in a final direction to stop this whole thing from rotating around, flopping around in space. That's problematic. It's problematic because it's very difficult to decide exactly where that node or those three nodes should be without affecting the rest of the simulation that you're really interested in. You can take a wild guess and constrain it. Let's see what we've done here. You could take a wild guess and constrain it maybe at the center of mass, like I've done here. So what I have done is make a little surface, and I've inserted that surface into the assembly. You can see here I've got a surface there, and I've got my other one up there. Sorry, my airplane up here, and I've just fixed this surface. Now, it's as easy as that in Onshape to do this sort of constraint like this. And because of the settings that we've got, now if we open up the simulation panel, I'll talk about those settings as well. I have here a setting which is the connectivity, and it's saying that anything that is mated together or touching will be considered connected. All right? So because these two things are touching, they're going to be considered connected. And what I did to fix this was I simply right-clicked on it and said fix. Right? So that is the equivalent of putting a constraint on this. Now, if I put a load, and this is the force on the front of the plane, remember I'm trying to kind of replicate what's going on here. Here's the coordinate system, and here's the yellow load at the concentrated on the front here, pointing down. All right, so that's what I'm doing here. And I've constrained it because unless I have a constraint, I'm not going to be able to solve this solution. Have a solution. In fact, if we just have a look at this, you can see now I've got a result, and so far all I've got really is a pretty picture. You can't trust this for accuracy or for correctness until you do a lot more thinking. And let's do some of that thinking now. Now, yes, we have constrained this so there is no motion at this face here. But you see the whole plane is rotating around that point. And that's because there's none of the mass of the rest of this plane is contributing to the restricting any of this motion. So let's fast forward and call something. The topic of this is inertial relief or inertia relief, depending on your definition of the term. Inertial or inertia, it's all the same. Inertia meaning something that has mass, and relief meaning it's going to relieve some of the stress, some of the deformation, some of the strain due to the effect of that mass having to accelerate. That's what inertia is all about. So how do you do that in a simulation? If you have a look at tools like Abacus and Nastran, this is Nastran with the NX Nastran with a FEMAP front end. This is ANSYS. All do it the same way. In fact, if we have a look in here, there's an additional step that is required, which is to create a load. In this case, it's an inertial relief load, and we have to define a bunch of things, which are the free directions. And in the case of FEMAP with NX Nastran, here we have to define an INREL or INREL with an additional parameter. That same thing is relevant over here in HyperWorks, in HyperWorks here, INREL with a -2 parameter. So all of that is kind of complicated, and let's see what it takes to do that in Onshape now. So let's take our same aeroplane model. In this case, you see it's already solving for me. I have my load. This is the same load as before. But what you'll notice is that there's no constraint underneath there. That's just the split of the face. There's no constraint on there. There's no other parts. There's a single part in this entire simulation. That's all there is. The only thing that I had to do was toggle the inertial relief option in the simulation setup. And this told the solver all it needed to know in order to go ahead and run the simulation. Now, if we have a look at the results, and we're looking at displacements here, and I animate them, you kind of get this sort of intuitive, now you realize that, well, if this thing is going to start moving down, then these big, heavy end points are going to try and move in sort of to counteract that. And that's exactly what inertial relief is doing. If you think about a very, very simple equation here. Normally, when you are solving a linear static analysis, the sum of the forces need to add up to 0. Now, the constraint here is providing some of these reaction forces. So the sum of the reaction forces here and here have to come up to 0, right? When we don't have a constraint, we need something else to provide those cancelling out forces, so the thing doesn't fly around in free space, right? Remember, this thing, in this case, is no longer constrained, so how are we going to stop it from flying, so to speak? That's what inertial relief is about. The inertial relief is going to analyze the rigid body modes and provide an equivalent acceleration which cancels out the forces that are being applied to the model. So these forces don't have to be, you've got one force here which has got nothing else cancelling it out except for the inertial relief terms that are going to be automatically applied to the body. Now, this is why, of course, and any FEA requires this anyway, but it has to have mass, right? This part has to have mass properties such that the acceleration term can provide the forces to cancel out this. So, very simple example like this. The problem is with this example is that this is not very practical for most people. And you see that, it's kind of like it is the example that often is shown, satellites, spacecraft, airplanes. But what we're trying to do here, in fact, is bring this back down to something that more mechanical engineers that are probably on land-based projects might understand as well. So for that, let's have a look at the internals of an engine like this. Now, this could be the same as the example that Neil showed in the
Inertial relief.
in the video here, where we've got a reciprocating conrod inside this jackhammer. But in my case, it's a little aircraft engine. So we've got the piston, the conrod, and the crank turning around. Now, at any point in time, there is a force being put onto the conrod by the piston because it's getting the explosion ahead of it up top here, and then there's also a reaction force imparted on the conrod by the crankshaft as it spins. So you think about there's two reaction forces imparting on this conrod, and at any one particular time they don't have to be. They're not equal and opposite. This thing is not going to, if we just took those two forces and applied them there would still be rigid body motion in this system. All right? And so we're going to need something else to constrain this conrod when we try and simulate it. So if we take a conrod here, and I'm just going to put two arbitrary bearing loads on this. You see here there's a bearing load on the top, and you can see the direction, the components of that force here, and you can see the direction definitely not equal and opposite to the one on the bottom. So if we tried to do a linear static analysis of this, well, we couldn't yet. We would have to do a bunch more. We would have to put another part or two in here. We'd have to do some constraints. And it's those constraints which are really the problematic part, because how do we put those constraints in here without giving it over constraining it in some direction, or making something too stiff that doesn't have real life constraints on it. This is the case for inertial relief. In fact, anything that is under constrained can be solved using an inertial relief, and we've got one more example here to do that. So we've got this model. We've got the single part. We've got the two loads, equal and not equal, not opposite. We have turned on the inertial relief option. You can see here that I've just got the two bearing loads on it. And if we show the results on that, you end up with a sort of an intuitive kind of bending deformation. If I just look at displacement there, as this thing is moving up, the mass of this is going to try and continue it moving in sort of one direction, and it kind of deforms out in that direction. All right, so this is going to be a constantly changing thing. So what an inertial relief analysis with linear static analysis is really doing is turning a dynamic situation into a quasi-static situation, and that's really one of the other keys to this. Now, it's not applicable if the frequency of change of these directions is at the sort of the resonance frequency or the first fundamental frequency of the part. This doesn't take the place of a true dynamic analysis. It turns something into a quasi-static analysis, as I said, and which is a much, much simpler problem to solve. And certainly, if you are away from those fundamental frequencies, then it's certainly a valid use of this type of technology. All right, so that is with this free situation. Normally, this thing has 6 rigid modes. this has removed those rigid modes. It's applied the inertial force acceleration as a force to the body to make sure it remains in place, and we can get a good result out of that. Now, where this gets even more interesting is with a situation like this. This is a lower control arm of a typical front-wheel drive car. We have a end of the lower control arm which is fixed to the chassis. There's some other attachment points for various things that we don't need to worry about. This here is where there's a giant bushing where the strut, there's a McPherson strut or shock absorber and spring goes up on this. And then up this end there is a ball joint, the lower ball joint of the wheel hub of the knuckle here, which where the road loads or the loads from the wheel would be imparted. So just as the Conrod example, these loads aren't necessarily equal and opposite at any particular time in an event as the suspension is moving. And I say it's moving because if you have a look here, we have a revolute joint connecting the lower control arm with the chassis. So I've got a part here which is just a surface at the moment. So that's one part which represents the chassis. There's obviously the chassis is much bigger than this little cylindrical part, but this is just enough to do the analysis. So I've got this one part and I've fixed that. You can see here the part is fixed. I've then created a revolute joint using a mate, the revolute between the lower control arm and the chassis. So this means that this lower control arm is free to move in this 1 degree of freedom. Now, if we did an analysis now, it wouldn't solve because it would tell us there is a rigid body motion, and in fact, let's run that. If I turn off this option for inertial relief and try and run it, it's going to try and start the analysis. It's looking at it now, and pretty soon it's going to come up with an error that says you cannot run this. And we already know that because I've just told you, but it says here that it cannot converge. Please consider a different connection type, or, and this is the important new thing, apply inertial relief to address the rigid body motion. Okay, so applying inertial relief to address the rigid body motion is very simple. Of course, all you do is hit that button there. So just as in all of the examples here, from whether it was the aircraft flying in free space or the Conrod, which has got 2 unequal loads on each end, or in this case where we've got 1 degree of freedom still free, applying inertial relief is going to calculate the required acceleration that's going to be imparted on this body, such that this thing is no longer in this situation of free rotation. So if I put the deformation up somewhat, you can see here we've got somewhat. This is the kind of the motion that we're expecting. This thing is not over constrained at this end. See, this thing is allowed to rotate. All right, this is allowed to rotate at the body to chassis connection. We've got our load put up from the ball joint. We've got the load put down from the strut, and this thing is deforming. This is a really cool, easy to use and easy to understand, a kind of intuitive way to use inertial relief. And as you can see, it's a really easy thing to do in Onshape as of January 27, 2025. June 27, 2025, sorry. No, the year's getting away from me. I think that is that's probably all I wanted to show for now. There's many examples where an under-constrained situation can be helped by inertial relief. And the question to always ask is like, well, if you don't know those constraints and you just keep putting things in to make things solve for a linear static analysis, you really have to be careful, because you may be over-constraining the situation. You may be imparting stiffness into the part that doesn't exist in the real life, and therefore rendering your initial simulation completely invalid. In those situations, inertial relief can be a really, really good technique to address that.